All right, so here is that first part. This is that part of the graph. This is that part of the graph where he goes up here at the beginning, and he kind of comes around and back down, and then does a whole bunch of other stuff, right? So again, what we have to make sure we understand is that we have an x equation and a y equation that are for the x and y coordinates of this at a certain time. Okay, so parametric equations is nothing more than an equation that tells you about this movement and an equation that tells you about this movement. That's what it is. Okay, that's what it is. And so when you put those two movements together, that's when you get diagonal movement, right? That's two-dimensional movement. So you've got some horizontal components and vertical components. If there's only one dimension, then if one of these is 0, if I let y be 0, I would just have a normal, regular kind of one-dimensional motion, like the Bismarck problem. Like we could say x of t equals t cubed minus 3t plus 7, and y equals 0. We could actually graph that. And what's cool about that, actually in parametric mode, if you graph something like that and then trace, you can actually see the movement. You know what I mean? If you did a regular time distance graph, it would, if he was going away from Bismarck, it would go up, and then towards Bismarck, it would go down, right? That kind of thing. That's what it would look like, because over time, he's traveling some distance. But if you graphed it like this, all you would see was your dot just moving back and forth on the x-axis, right? Because the y would always be 0. So that would actually model. So the cool thing about parametric motion is it actually models the movement. It shows where the particle is at different times. Okay, so you could trace, and so what you see is you see your trace dot going this way, and then if it stopped, and then if it went back, and then it would go this way, and then it would do that, right? You would see that kind of graph instead of, going away from Bismarck and then towards Bismarck and away from Bismarck and towards Bismarck, you know what I mean? And then go negative would be left of Bismarck. You actually can see the dot like it's moving. So parametric is really used to model that kind of motion. And it can also then model two-dimensional motion, right, like we're doing here. So this is just like you're looking down from above on a piece of paper, and this bug is like crawling around. That's what you're seeing. You're seeing its actual location. So that's what's cool about parametric graphs. So what I've got here then is I've got this, I've just zoomed way in on this particular graph, okay? And I want to trace, and so answering some of the questions, what was question 5? It says, when does he first start to head back or something like that? Or no, when does he first get back to the y-axis? The x-axis, was it like 1.7 or something?
At what t does he turn around?
Yeah, what value approximately does he turn around? Well, if you zoom way in, you can kind of see. Now, where's he turning around? Right in here somewhere, right? And what does that mean, turn around? Well, it's kind of a U-turn. So right in there. So I don't know, 0.83 or something, right? That would be, and I've set my t-step, and I went into my window. You may have noticed this. We went from 0 to 4 pi. Remember that on our t? Well, if you really need to go ahead and change your t to 0 to about 1.7. That's what they were talking about when they said, reset the window. You're supposed to sketch that graph on number 6. You're supposed to reset the window so it only went from about 0 to 1.7 or so when he comes back down. Okay, and so then you could set your t-step to like 0.01. Anyway, none of that's going to be that huge of a deal for what we have to do on our next quiz. But so about there. Okay, so then you got to question 7, and it says, find precisely when the y stops increasing and y starts decreasing. Well, that's what we were talking about yesterday. That's right up here at this top peak, right? Right there. Okay, well, the slope of the path is 0. Now, we said the slope of the path is going to be y prime over x prime, right? Well, when is that ever 0? Well, when the top is 0, when y prime is 0. So what you were supposed to do is just take your y prime equation, do a solve. So let's do that real quick. Tell me what your y prime equation, I just want to run through this with you one time. So tell me what your y prime equation was. Hang on, let me get to my solve. All right, what do you got?
0.3 plus 4 times side 2 times x.
Okay. And so that's y prime, and we want to know when that equals 0, and then I have to put a comma x, and then it would be helpful to do the vertical bar and put the vertical bar in and do between 0 and where does it happen? We just saw about 0.8 something, right? So between 0 and 1 would be a good place to look, because otherwise you're going to, whenever you solve a cosine or a sine thing, you're always going to get that that other goofy stuff. So you just, from here on out, you just need to know when you do a solve. I mean, I answered this question for a lot of people, but you got to understand when you do a solve with a trig function, especially if you get all these other answers, you got to think, okay, what am I solving? What's my input? It's x. What x's do I want to limit it to? Here, x is our t, and our t is the time, and we only want to look in this small amount of time here at about 0.8, right? So between 0 and 1. So I'm going to hit enter, and there it is exactly, right? That's when it got to that 0.8229 or 823, okay? And so that would be your answer that you would want for that one, okay? Now, number 8, so one of the big things you're going to have to do in our next quiz with parametric equations, you're going to have to be able to put one into a graph, you're going to have to be able to trace around on it, okay, at various times. You're going to have to be able to see the direction that it travels, right? One of the things you're going to do on your homework today is sketch little graphs, and you're going to mark with arrows what direction it travels, plot at certain times. You might have to solve, right? We're going to do a practice one here in a second. So, okay, number 8 then says, is he stopped or is he still moving? Now, how could you show that, though? Right? He stopped doing what? Stop going up, right? Stop going up. But he's still moving to the right. But how can we show it?
You could put the t value into the x prime equation.
That's what I would do. Or you could also set x prime equal to 0 and solve and see if you get 0.822. Now see if you get that same number, right? But I like what you're saying. So a really good way to do that would be to just take, because we've talked about this, what was x prime? What's x prime? Tell me what x prime is. 0.4 cosine.
T. And then minus 0.4 times t times sine.
This is x prime.
Yeah. Might as well put x.
I'll put t's. No, you can put t's. Doesn't matter. T times.
Sine.
Oh yeah, because we had to do a product. Now notice how I'm not doing a solve here though, right? What am I trying to do? I'm trying to plug in that number right there. Now I probably should have used x because I can grab that, but now what do? I do a vertical bar. That means width, and then I'm going to arrow up. I'm going to actually arrow up. I don't have to arrow up right now, but I'm going to arrow up and grab that. Hit enter. Now I don't want that to say t. I want that to say x. Or excuse me, I don't want to say x, I want to say t. But right, remember how we did that? That's how I can plug that number into an expression. So one thing is solving, so you're setting it equal to something and solving, but if I want to plug a number into an expression, this is one way to do it, right? This is one way to do it. I could have just typed it out too, it doesn't matter. But this is one way to do it, okay? And so there you go. Now, it's barely moving, and it's moving what direction? Because since that's positive. Since x prime is positive, it means its x movement, its horizontal movement, is to the right. But it's barely moving, so it's almost stopped, but it's not quite.
So if you get something other than 0, then that means it is still.
That's right, because what is x prime? What does x prime represent? Horizontal velocity. Horizontal velocity, and y prime is vertical velocity, right? So it's negative, it's moving to the left, positive. So if you get something other than 0, it means it has velocity. So it means it's moving, right? If you get 0, it means it's not moving in that direction. So we know it's not moving up at that instant, at that time value. This is a time value right here. It's not moving up, but it is moving to the right, just barely. We're moving very slowly, but it is moving. Okay, so that's all I really wanted to talk about on that. We did talk about on number 9, it said zoom in. And so that's what I've done here. So you can zoom in and you can kind of see that that's what's going on. Okay, they said the zoom box. What the zoom box is when you didn't have to do zoom box, but zoom box works really good on the computer, as a matter of fact, because I can just drag. But what you have to do is you have to you have to move your cursor up here, hit enter, and that'll be a corner, and then you can drag over to here, and then you can just, you kind of do that. Drag that as a box. That's what that is. Okay? All right. Anyway, let's go, let's move on. So go ahead and get your notes out, and this is the stuff we wrote up here yesterday. Okay? So, I don't know, because we're going to do section 3, section 4. It's probably not next week, probably the week after.
Are we gonna have any parametric stuff on the
I don't think so. I think the parametric stuff's pretty much all calculated stuff, right? So, now, here's what, I mean, this is just real basic knowledge, right? Got to know this, that what does X and Y represent? I mean, this is what we wrote down yesterday. X and Y is the horizontal and the vertical coordinate of the graph, right? And then X prime, Y prime is the horizontal and vertical velocity on the path of whatever the object is, okay? That's the movement horizontally and vertically. Now, we combine those then in two different ways. One is to get the slope of the path. You just take Y prime divided by X prime. Now, that could be an equation, or then if you want the slope at a certain point, you plug in. Right? You plug something into it. So you've got to know that slope of the path. So if the question's about the slope of the path, slope of the parametric graph, then that's Y prime over X prime. If you want the speed of the object on the path, then you do that. That's the square root of X prime squared plus Y prime squared. You got to know those two. You just got to know those two. That's about all I'm going to ask you. So in your notes, I want you to do this problem right here. I want you to do all that. I want you to graph this. I'm going to give you a little time here. I want you to graph this with that X and Y, and I've given you the T. I want you to find the horizontal velocity of 2. I want you to find the vertical velocity of 2. I want you to find the slope of the path of 2. I want you to find the speed of the object of 2. You got to do all that. Those are all things we have to be able to do in the quiz. Is this a graph you had? Now notice, because I've got other graphs in here, mine's in X4 and Y4, right? Instead of X1 and Y1, right? Because I got some other graphs in there that I've hidden. Okay, but this is the base. So I gave you the window because I didn't want to. Now, sometimes you have to do the window, right? Now, why would I know this is a good window? Well, what's the outputs on cosine? No. 0 to 1?
Oh.
What are the outputs on cosine? What's the range on cosine? There you go. -1 to 1, right? Cosine, -1 to 1. Then you times it by 3. -3 to 3. So X is going to need to be -3 to 3, right? So I set it -5 to 5, right? So you should have been able to figure this out on your own to set yourself a decent window. What can sine be? -1 to 1. But if I add -2 to it, that'd be -3 to -1, right? So -3 to -1. So I set mine from -5 to 0. So I had a little extra space there, right? So it wasn't rocket science really to figure out that's what the window needed to be, right? You just look at the function, you say, well, what are the possible, like domain and range, right? That's all it is, domain and range. Okay, that gives you what your x's are, what your y's are, because that's what these equations are. That's the x coordinates, that's the y coordinates. So we can set our x window much easier, actually, when we're doing something like that. Now, what's the t range? That just depends. How long do I want this object to be moving around, right? And I just did 0 to 5, and I gave you a pretty nice little picture. Now, anyway, so we can trace and write, and so I would want you to be able to go on here. I want you to be able to trace, I want you to be able to trace to the right and tell the direction of travel. So we can come on here and put little arrows, right? I'd have you maybe go to 1 or whatever, trace to 1 or 2. Here's 1. I might say trace to 1. Well, here's 1 right here, t equals 1. And then put a little arrow showing the direction of travel, right? I might want you to label some points to be able to do that, right? So you need to be able to trace and do that on a graph. All right, so calculating these things, actually, here's what I did. I just, since I had it stored in X1, X4, and Y4, I just let the calculator do the derivative. I did it with respect to t, right? Now, They were easy derivatives. You probably did it on your own without, but that's what I did. So there's x prime, there's y, right? Then I need to plug in a 2. Now, it would have been faster to just put a 2 there for that t, right? When I typed this in, I could have just done negative 12. But what I did is I grabbed that. I could have deleted the t and put a 2, but I did the vertical bar and plugged in a 2, right? Same thing. So I plugged in 2. Is that what you guys got for horizontal velocity? Vertical velocity? Right? So what direction, now here's another question I'd ask you. What direction is this going at 2? What direction is this going? Left and up. So this is going left and up at t equals 2 because the vertical velocity is negative, horizontal velocity is positive. So that's another question I could ask you. Okay? Here's the slope. Right? Now, think about that. If it's going up and left, wouldn't that be a negative slope? Isn't that a negative slope? It's going up and left. Now, is it going up and is it going more up or more left? Why? Okay, number one, it's got a pretty small slope, right? The slope's pretty flat. So it's going more left. But I like what you guys said too. It's got a lot more horizontal velocity going left than it does upward velocity. So that's a factor. Well, of course that's a factor because we divided this by this, right? So if you've got a lot bigger number for x prime, that's on the bottom, you're going to get a lot smaller fraction for your slope, and it's going to be more level, right? Okay, so it all makes sense. It all works together. And then here's the speed. Now I had to put parentheses because this was negative. I had to put parentheses around this and try to square it. That would have been bad, right? Because that would have been negative 3 squared. What's the calculator going to get for negative 3 squared? It's going to get negative 9. Because it's going to say, please excuse my dear Aunt Sally, and it's going to think of this as a negative 1 times 3 squared. And it's going to think of the exponent comes before the multiplication. So if you type in negative 3 squared, just try it right now in your calculator. Type in negative 3 squared, hit the squared button, do negative 3 squared, I'll bet you get negative 9. You do, don't you? Right? It's just like negative x squared. What is negative x squared the same as x squared? No. It's a negative 1 times x squared. So negative 3 squared is negative 1 times 3 squared, right? You've got to put that in parentheses, right? So if I hadn't put that in parentheses, the biggest mistake people make is somebody's going to do it on the quiz next week or whenever we have it, I'll guarantee it. So when you take your x prime, make sure if it's negative, make sure you put parentheses around. So x prime squared, y prime squared to the square root, that's how fast it's moving. Now that makes sense because it's got this much velocity going that way, plus it's got a little more up velocity too. Doesn't it make sense that this velocity be bigger than either one of these two? Right? Doesn't that seem reasonable that that's about the velocity of this object because it's going this way 11 and it's going up some also about 2. So those two combine to make a total velocity, total speed of 12. All right. You've got to be able to do all those things with parametric equations. Graph, understand the velocity, direction of travel, all that stuff. Okay, now we're going to get into just a couple other things with parametric equations. So on our calculator, and you can do this with me or you can just watch. It doesn't really matter. I'm going to go pretty quick with it. And so it doesn't really probably matter that you can do this. So what I've done is I've graphed this right here. Now think about this. If I tell you that x is equal to t, and I tell you that y is equal to t squared, okay? Now, just think substitution. Just think substitution. If x and t are equal, doesn't it mean they're interchangeable? Right? X is always equal to t. So at 1 second, the x coordinate will be 1. At 2 seconds, the x coordinate will be 2. At 3 seconds, the x coordinate will be 2. Right? X and t are interchangeable. So doesn't that make sense that I could then take this t, this x right here, and sub it in right there for that t? And what would I get here? Y equals x squared. Wow, look at that graph. That's called eliminating the parameter. By substituting, by taking one of these and substituting in the other one, we get a normal function for the graph. Now look at another one we've talked about recently. X equals cosine t and y equals sine t. Remember how that was a unit circle with a radius of 1? Let me square both of those. Right, so wouldn't this have to be true right here if you squared both of those? Wouldn't x squared be cosine squared and y squared be cosine squared? Now let's add those two together. Let's add x squared plus y squared together. Right? that would be cosine squared plus sine squared. Oh, what's that? We know cosine squared plus sine squared is 1, right? So in this particular graph, we'd have this right here. Oh, what is that the equation? Center, 0, 0, radius, oh, the unit circle. Not surprising, right? Not surprising. That's called eliminating the parameters. So this is the equation of a circle centered at the origin, radius 1. We do a little bit of work with it, combine some things. We get the regular, without the t in it, right? Eliminating the parameter. But it's nice to have the parameter. So I want you to see that connection between these graphs. So it's easy to predict that this is going to give us the graph of y equals t squared. Now, I want you to look at something here. Look at this black graph. X equals t cubed and y equals t to the 6th. Notice how it's the same graph. Well, look what happens when I do that same thing. If x is equal to t cubed and y is equal to t to the 6th, but isn't t to the 6th just t cubed squared? So if x is equal to t cubed, couldn't I substitute an x right there? And couldn't this be y equals, oh, it's the same graph. Isn't that interesting? But remember when I don't know if I mentioned this to you guys, but we were talking about the path yesterday, and you could have the same path, but two different people running on the path, and one would run faster than the other. So we got the slope of the path, and we got the speed of the path. Well, that's what's going on with this. If I trace on this graph, okay, so right here, let's go to 1. So on the black graph, when t's a 1, you get 1, 1. On the red graph, when we go to 1, of course it's at the same point. Well, that makes sense, right? So it's kind of like they're tied, right? They're at the same place. But now let's go on the red graph. Now watch the red graph. 1.2, 1.3, 1.4, 1.5, right? See that? Now let's go to the black graph. 1.1, 1.2, 1.3, 1.4, 1.5. What do you notice? It's going a lot faster, isn't it? It's at different places, right? Well, it makes sense because at 1.1, 1.2, 1.3, right, the x is getting bigger because it's t cubed. Here it's just t. Same path, though, because if we eliminate the parameter, so this looks like two different things, but if we eliminate the parameter, make a little substitution in there, then all of a sudden we see that it's the same path, but two different objects on the path, right? So their speeds would be different at different times. And the slopes would be different too at different times. That's just it. The slopes would be the same at the same x and y locations, but at different times the slopes would be different because there would be different places on the path. So we could make an infinite number of these, right? I mean, we could make a whole bunch of these. It would all be y equals x squared, but they would do that. But it also shows you a neat way you can use parametrics for just any old graph. If I want to draw the sine graph with parametrics, all I would have to do is do x equals what? If I want to draw the sine graph with parametrics, x equals, look at this example right here. X equals t and y equals sine t. And that would give me the sine graph. Because I could interchange the x and the t, I could put an x right there and get sine x, right? I want to do the cosine graph with parametrics, I do x equals t, and I do y equals cosine t. And that would be the cosine graph in parametrics, right? You just let x equal t, right? Okay, so onward. So that's one thing. Okay, so let's say we had this right here. Okay, now this you might want to write into your notes. So you got x equals 2 minus 3t, you got y equals 4t minus 1. Now those are both linear situations. When you get a situation like this, then you are going to get a linear graph. Okay, now it's going to be a line segment because you're going to have t, right? You're going to have a limited t just like our line and ranger. This would be just like our line and ranger. Remember our line and ranger equations, and they were both linear kinds of things, and then they made a line. But what line do they make? Well, here's where we can eliminate the parameter. Well, we would just do substitution. So what I would do is I would take this equation, and I would subtract 2, and you might do this with me because I think there's a couple of your first few homework problems do this. They're linear and they tell you to eliminate the parameter. Or I think it says write it as a function in terms of x, y in terms of x. So now I'm going to divide by -3. Now I'm going to write that -1/3 x plus 2/3. That would equal t, right? And then what can I do with that? I'm going to take that and substitute it in for that t right there. So you get y equals 4 times -1/3 x plus 2/3. So it's kind of like a 2 equations, 2 unknowns kind of thing. Minus 1. So I just plug that in for that t. So I'm going to get y equals -4/3 x plus 8/3 minus 1, which is y equals -4/3 x. This would be 8/3 minus 3/3, that'd be 5/3. So that's the line it would actually make right there. If I did this parametric graph on my calculator, it would give me this line right here. Okay, but that would just be the path, right? See, this is the disadvantage to if we're modeling motion, if we're actually modeling motion. This equation just gives me the path. It's like that parabola, right? I had two different equations. They both have the same path, but the two different equations represented different objects on the path. So we can model the actual motion. So this just tells me the path. This equation, though, actually gives me where the object is, what its x and y coordinates are at certain times. So that's why it's a parametric equation, a good way of modeling motion. Okay, because it brings in the time element. Okay. All right. So inverse functions. I'm probably not going to put much on the test, but there might be something in the homework about it. So just a quick thought. Remember I asked you guys about this when we were doing inverse trig functions. What is the first thing that comes to mind if you're thinking about a graph of an inverse function? Switch the x and the y. Isn't that perfectly suited for parametric equations? Because you have an x and a y equation. So what graph would this be right here? We've already seen it. What does that graph look like? Well, no, this one. This would be y equals x squared, which is going to be a parabola. Well, what is the inverse of y equals x squared? But it's if you square root both sides, right? So what do? We interchange the x and the y. We get this. We square root both sides. It'd be plus or minus, right? It's not a function. And so if we want to graph that, so it'd be a sideways parabola, right? Like that. Square root's just the top half, right? But it'd be plus or minus square root. Now the problem is that's not a function. If I wanted to graph it on my calculator, I would have to graph both parts, right? I'd have to do two graphs, right? The top half and the bottom half in function mode. The nice thing about parametric equations is all I got to do is switch them around. All I got to do is x equals t squared and y equals t. Now let me go back to my calculator and I'll just do that real quick. So if I go here, let me make that t squared and let me make this one t. And look at that. Boom. In one thing, I get the inverse function, right? So like arc sine, you want to do arc sine, really just do x equals sine and y equals t. Now, big deal, that's not a huge deal, but here's where it could be a big deal. Because when you say interchange the x and the y, what do you want to do? You'd want to do this, right? You'd want to go 3y cubed minus 2y squared plus 1, and then you'd want to do what? Solve for y. Can you solve that for y? There's no way. There's no algebraic way you can solve that for y. You can't do it. So it's a really hard thing to try to do the inverse function of. But what would we do? To do it normally, we just do x equals t and y equals 3t cubed minus 2t squared plus 1. That'd be the normal cubic graph, and then we just interchange those. X equals 3t cubed minus 2t squared plus 1. And y equals t. We just interchange those, and that would be the inverse of that function. Okay? That would be the inverse of that function. So parametrics can just be a neat way to graph a parametric thing. I just pretty much throw that out there as just kind of a, hey, here's something that can happen with parametric equations. Since you have an x and a y equation, you know, That's not a bad way to do something. But we're not going to get into that. In Calc 2, they do, I mean, we get right up to the borderline. We do a little bit of work with parametrics, but in Calc 2, then they go in to do more with it, a little more with the parametrics and so forth. But I like to kind of introduce it and see it. It's not something that's on the AP test. So in our packets, midterm, final, you won't see anything about parametric equations, okay? But we do have a section or two here in our book on it. I think it's a good kind of introduction to that. And it kind of fits in with some other stuff we're doing anyway. So, all right. Last thing. On page 247, example 10. Now, on your homework, the last like 3 questions on your homework all refer to this problem. So I want to go through it with you, get it started with you. So we can. So on your homework, you're going to have some problems initially. So we did the thing where we were tracing, we were graphing, we were tracing, we were finding the horizontal velocity, the vertical velocity, that kind of thing. So we got to be able to do that. On your homework, you're going to have some of this, right? You're going to have some of this right here, right? With the eliminate the parameter, maybe solve for t, right? They're maybe going to have you graph it on your calculator first. Maybe you're going to graph it on your calculator. One thing I know they say, where's the starting point? Where's the ending point? Well, if I gave you this graph and told you that, and you were going to graph it, say, from here to here, right? And they wanted to know the starting point and the ending point, what would you do? You plug 0 into both, and you get 2. Wouldn't that be the starting point? I mean, you got to understand, remember, that this is x and y. They're coordinates. So you put a 0 into here, you get 2. Put a 0 into here, you get 1. That's where that line's going to start. And where's it going to end? Put a 4 in, right? 2 minus 12 is negative 10. And 16 minus 1 is 15. So this is going to be a line that's going to start at 2, negative 1. It's going to end. Because, again, it just gets to your understanding of what these things represent. The t's represent the time, right? So it's going to begin at that, and it's going to end at that. And you just plug those values in to get your x and your y, which are your coordinates on your graph. Okay, so you just got to understand what those things represent. All right, so that's going to be a big part of your homework, is doing this kind of stuff with this. There's an example in your book that talks about, before we do this problem, there's another example in your book that gives a goofy kind of graph, whatever, and it gives dots every 1 second. Okay? Like this. So this might be t equals 1, and this might be t equals 2. This is one of your examples in the book. It's something like that. Well, and they ask you some questions like this, like how can you tell when this object is moving fast, and how can you tell when it's moving slow? How can you tell when this object is moving fast, when it's moving slow? How far apart the dots are, right? Because that represents like every second. Right? So that's kind of velocity, right? That's kind of how fast. So the bigger gap between the dots, if they're all 1 second apart, the bigger the gap, the faster it's moving. The smaller the gap, the slower it's moving, right? I mean, that's just again, kind of some common sense stuff that it talks about there. Okay, back to this problem. So we have a pitcher throwing the ball. I worked hard on this. Pitcher throwing the ball, and he's going to release the ball from a height of 7 feet, right? So he's about 6 foot tall, maybe whatever, a little less. So he's pitching. We're going to say he's going to release the ball straight ahead, which probably is not accurate, but anyway. Okay, so he's going to release the ball when it's straight over his head, right? And the pitcher's mound is 60 feet 6 inches from home plate, right? So that is 60.5 feet right there. He's going to release it with an initial velocity, and so it's going to be straight over his head. So he's going to release it exactly horizontally. We're making this easy on ourselves, right? So exactly horizontally, 150 feet per second. Now, what's the ball going to do? It's going to drop because of gravity, right? Because of gravity, it's going to drop. Now, we're going to assume that there is no wind resistance, right? So the only thing going to cause this ball to drop is gravity, right? But the other thing that affects it is the air resistance too. So we're going to eliminate that to make our equation simple. Now, one of your homework problems says, okay, let's do it without ignoring that. And let's factor in wind resistance. And they give you the equation, so, right, you just have to work with it. We're going to build the equation just really quickly. Now, because we have shorter time, I'm not going to spend as much time talking about it. But the X equation, now remember, this is feet now, right? The X equation, since he throws it at 150 feet per second and there's no wind resistance, isn't this ball going to go after 1 second? It should go how far? 150 feet. After 2 seconds, 300 feet, right? Horizontally now I'm talking about, right? It's also dropping, but horizontally, if it's got a speed of 150 feet per second, there's nothing slowing it down, no wind resistance. The equation is just going to be 150 T, right? So we're going to let this be, this is going to be 0, this is going to be, X is 0, right? This is going to be 60.5 right here. Okay, so this is like our origin, this would be like maybe your y-axis right here. So it'll be 150 feet after 1 second, 300 feet after 2 seconds, which obviously it doesn't take that long to get the whole plate, right? So we're talking less than a second here. But that's going to be our X equation, so pretty easy to figure. The Y equation is going to be different. Now remember, Y is the height of the ball, right? Y is the vertical distance, right? Y is the vertical distance. Now at time 0, what's the ball's vertical distance? 7, right? 7. The vertical distance is 7. But then every second it's going to drop how much? Well, its velocity is going to drop 32 feet. So maybe I should do that first. So actually, don't write this down, don't worry about it. But what's going to happen here is the ball's going to start with 0 vertical velocity, right? Because it's only going horizontal. So it has no vertical velocity. So, oops, I don't want that. So y prime is going to start off with 0 vertical velocity, but then it's going to lose 32 feet per second every second, right? Now let's do the antiderivative of that, which will give us y, right? So the antiderivative, we raise that to a 2, divide by 2, so that'd be negative 16t squared plus c. What would c be? The second, right? Because at time 0, the y value, the y is the distance, the y vertical distance has to be 7. So this equation is going to be 7 minus 16t squared, or negative 16t squared plus 7. Okay, so I don't expect you to come up with that. It's not hard to figure where that comes from. But there we have a parametric equation for this ball. So if you graph this then and set an appropriate window so you can see it, your x would have to be at least this long, your y would have to be at least enough to see 0 to 7. You could see this ball drop. Okay, now some of the questions, well, the question that is asked on page 247 is, when does it cross a plate? At what speed does it cross a plate? Is it a strike? And where does it land? So we can get all of that information from here, right? Now the first thing we probably want is what? First thing we want to do is get our derivatives, right? So we want x prime, which is 150, and y prime, which is negative 32t. So the first thing we should probably do is figure out when does it cross the plate, okay? So using those equations and know what they represent, what would we have to do to see when it crosses the plate?
Set the original.
Not x prime, because that's the velocity, right? X prime is a horizontal velocity. No, that's 150. Set the x equal to 60.5. We want to know when x is 60.5. So 150t equals 60.5. Divide that out for me real quick. Now that's going to be a key number for us because everything else is going to be based on that, right? Because everything we're interested in, except for where does it land, everything we're interested in happens when it crosses the plate. Like, is it a strike and, right, that kind of thing. So they wanted to know at what speed does it cross the plate. Isn't that bad? So this one's 150 all the time, so we don't have to plug anything in, right? So 150 squared plus, and then we would take negative 32 times 0.403, right? And we would square all that, right? So we would plug in a 0.403 into our y prime times negative 32. We would square that. What do you get? 100 what? 150.553. Is that right? Are we sure? You mean it's going faster when it gets to there than when he released it? Why?
It's like a triangle.
Well, we're ignoring wind resistance, right? So it's going to keep going horizontally at 150 feet per second, and gravity's pulling it down. So that's actually speeding it up, right? So so as it's coming down, it's kind of like you drop a ball; it speeds up as it goes. Yeah, so it's very unrealistic when you ignore wind resistance, right? For sure. Because what's that? And you release it right here, but that makes our y equation a little easier. But I mean, we can figure out what angle and how far in front. So we would, instead of 60.5, we'd have a little smaller number, and maybe the height wouldn't be quite as high, and so we could adjust that. But anyway, so it doesn't surprise us that we get a number that's actually going faster when it crosses. Now, so what equation would you use to see if it's a strike? Well, you would have to know the strike zone, but let's say we do. Let's say we know the strike zone.
Find the y.
It'd be this one, right? Well, at what? No, well, not at 60.5. At this time. We would take this time and we'd plug it right there, because that's the time when it crosses. See, so it's not hard, but it's just you got to think about what the different things represent. We want to know how high the ball is. Now, we're ignoring any left or right, as far inside or outside pitch, right? We're assuming it's going straight down the middle. So all we really care about is how high is it. So that's the y, right? And we want to do it when it crosses the plate, which is that time. So you put that time in there. What do you get? 4.4 feet.
That's
Might be a little high. Is this 4.5?
that seems a little. How tall are you?
Right. You'd have to know. I mean, I'm almost 6 foot.
Strike zones.
I'm shrinking.
Hips are knees to like chest.
It's supposed to be here. They kind of lowered it, but so that could be close. But you're right. You'd have to know the strike zone. You'd have to know the strike zone. Okay, to really answer that question. Okay, and I don't think it says it in there. So you'd have to know the strike zone. Okay, and then last one was, where does it land? If they all miss the ball, where would it land? When y is 0. When it hits the ground, the y is 0. Right? Now you could say when it hits the ground it stops, but maybe I don't think, because the equation doesn't know it stops, right? The equation would say it goes underground or something, right? So it's when y is 0 is what we do. And we set that equal to 0 to find the time. Now you're going to get 2 times because of the square. Well, one of the times is going to be back here, right? It's kind of a parabola. It's going to make a parabola. So it's going to give you a negative. It's going to give you a time back here that you would ignore. You have a negative time, that'll be another time. So that'll be the time, but if they want to know where does it land, then you'd have to put that in the x, right? The time would be when it lands. You'd put that back into the x to see how far it was when it landed, right? So just with those 2 equations, you can answer all of this stuff, right? Just solving them and setting them, and speed, using the speed equation. Only thing we didn't do was a slope, but who really cares about that? Okay, it's on your thing. It's 4-4 homework on the sheet, but you can skip 11 and 12. Well, 12 says in class, 11 didn't. So it was 11 and 12 on that assignment sheet you can skip. So it's 4-4, skip 11 and 12.
Do you have another one of those sheets?
Yeah.
These years? I don't know where it's at. I thought it was in my book.
Oh yeah, we got lunch now.
This is weird.
See my bear cat.